Hello, everyone, and welcome to another Saturday Science Home Edition. My name is Dan, and we're part of Discovery Outreach, supported by the Morgridge Institute for Research, WARF, and the University of Wisconsin-Madison. We're so happy to be here with you today. You can find out more about all the other activities at Saturday Science at the Discovery Building Facebook page or our website, discovery.wis.edu/Saturday Science. Remember, this and all the activities you do at Saturday Science should be done with the help of a responsible adult. Right now, I am so pleased to welcome our very special guests, Bassam Shahkashiri and Dr. Amanda, here with Science is Fun in the Lab of Shahkashiri. Take it away, Bassam.
Hello, everyone, and welcome to this very special program. This is the Overture, the William Tell Overture, and played by the Milwaukee Symphony Orchestra. We are today going to embark on an adventure, and I'm very happy to be with you wherever you are, in Madison, in Dane County, anywhere in Wisconsin, anywhere around the country. I know many of you are watching this program, and it's just delightful that we can do experiments together. We can learn together. And we have a special set of activities for you. Some will be done live, as you see right now here, and others have been pre-recorded. So I ask you to sit back and relax and pay close attention. If you pay attention, then you are more likely to learn than if you just meander around and look around. So let's go to the very first video where I want to show you some experiments done before.
My next experiment will be done using this burner, which is connected to the natural gas source. Can you see the flame? Not really, right? Can you see? I mean, I can see it, but it's not a good flame to watch. Let me see if I can make it appear a little better. So what I'm going to do is take a liquid from this spray bottle, and I'm going to spray it into the flame. Now you can see it better, right? How about if I take another liquid from a different spray bottle and do this? This and this. How about together? Well, what I have in this spray bottle is a water solution of table salt, sodium chloride. When I spray that, this is the color that we see. That's really cool also. All right. And if I take a solution of copper chloride and I spray that, I get this green. Now, you tell me, is this green the same as this green? Do they look the same? Huh? Kind of, right? What I really want to do now is spray this one that has the lithium chloride in it with this one that has boron in it in the dark. So if we take the lights down, there we go. 1, 2, there we go. All right.
The experiments that we just shared with you now, this is a very good experiment to remind us about the importance of movement of particles in the air. So when I'm speaking, I'm pushing air. And of course, it creates sound waves and it hits the microphone. The microphone sends a signal to you. If we were in person, the sound waves will hit your eardrum, and then something fabulous then happens after that. Signals are translated, sent to the brain, and we make sense out of them. But I want to emphasize the importance of wearing masks. Here's my mask right here now. And I want you to be careful and be thinking about the importance of protecting others and protecting yourself. Always set a good example. This is a display of what happens when someone is talking with and without a mask. So you be careful about that. And always, always be practicing good safety procedures. All right. Can we go back to the previous slide, Dan, please? So the colors that we saw were produced by chemicals. The red color, strontium salts, lithium salts, all of this is displayed in this visual. By the way, all this information is on my website, scifun.org, scifun.org. So now just watch with me and enjoy the presentation. You can go and look up more details as much as you want so that you can increase your knowledge and your appreciation of the beauty of chemical transformations. The orange color is due to calcium salts. The yellow color is due to sodium chloride, table salt. Green is a variety of compounds, including barium compounds. Blue is copper. Purple is a mixture of strontium and copper. And silver is produces the burning aluminum, titanium, or magnesium. So these compounds are used in fireworks, and fireworks are just a very special art. It's a very old art. It goes back to thousands of years. The whole idea is to lift the firework all the way up to the sky and not have it explode too soon. And then we see before we hear sound. That's another interesting part of that we learn about watching fireworks. So we move on now to the next slide, Dan, please. And this is to remind us that we in science and chemistry, we use symbols to represent the different chemicals. And here's a chemistry clock. And if you look closely, you can see that it is autographed. If you go to my website, it can tell you how you can get one. And can you tell time by looking at this clock? So hydrogen is 1, helium is 2. Have I given you enough hints about this? Oxygen is, what number is oxygen? Oxygen is 8, right? But it's a 24-hour clock. So we can make connections. That's what we like to do in science. We like to make connections between things that we know and things that we are learning. So this is a very useful device. It is actually a clock. It takes two batteries to make it work. This is just a still photograph of it. All right. So now we go on to the next slide. This is a picture taken at the Memorial Union Terrace in Madison, where around Independence Day, we've always done a program, attracted thousands of people, and we did the science of fireworks, expanding on what I have briefly shared with you just a few moments ago. You can see everybody, just look at the faces here. If you can, everybody's enjoying it. We are about to ignite a hydrogen and oxygen mixture, a gas mixture inside that red balloon. It releases energy in the form of light and, of course, in the form of sound. And when we do experiments, we always such experiments, we always obey the safety rules, and we wear our goggles as we do that. All right, so let's now go to the next slide, please, Dan. The next slide is a reminder of what the 4th of July celebrations are really about. The 4th of July is a celebration of Independence Day, the Declaration of Independence. And there are 3 documents that should be read all the time, but I make a point of reading them between May 24th and July 4th. The 3 documents are the Declaration of Independence, the U.S. Constitution, and the Bill of Rights. Why do I make a point of reading them between May 24th and July 4th? It's because on May 24th, I was sworn in as a U.S. citizen. And I look at these documents and look at them carefully. I do not take them for granted, and no one should take them for granted. They are the essence and the basis upon which our democratic society works. And I urge you to always look at them, study them, and to live what these documents mean to us today and how we want to be better members of society, respecting each other, working with each other, and doing good work for the betterment of society. All right, so now we go on to the uh, next part of the program. I'd like to invite a member of my group. She recently completed her PhD just last week. So I would like you at this time to welcome Dr. Amanda Shpijevak. So, hello, Amanda.
Hi.
I'm
Um,
happy you're here, and you have prepared an experiment for us. It's on video, but would you please introduce it?
sure. So the experiment that I want to do today, I think you were all told about beforehand potentially. So if you want to do the experiment along with me in video virtually, you'll need your vegetable oil and your Alka-Seltzer and your food coloring and some water now. And we'll go ahead and show that video so that you can make your own lava lamp. So what you'll need is some oil. I have vegetable oil, but any kind of cooking oil should be fine. Some water, so I just have some tap water. And then any kind of container. I think that wine glasses work the nicest, and I actually have a beaker wine glass that I'm going to use. And then lastly, some food coloring. I like green, so I'll be using that, and some Alka-Seltzer tablets if you have them. So I'll give you a second to go ahead and get your supplies if you have them on hand. If not, let's go ahead and move to the experiment. So the first thing you'll want to do is take your wine glass or other vessel of choice and add your oil. You're going to want to fill it about 3/4 full. So here's my oil in my glass. And then we'll add just a little bit of water, just enough to make a pool at the bottom. And you'll notice as we add our water that it actually sinks to the bottom of our glass. And that's because water is polar and oil is not, and also water is more dense than oil, so it stays at the bottom of our glass. There's something else that's more dense than oil as well, and that's our food coloring. So next, we'll add a few drops of our food coloring, and you'll notice that because it is more dense than our oil, it also sinks to the bottom of our glass. Okay, now, this experiment is going to make a lava lamp, which is pretty cool. Normally, lava lamps work by heating the oil that's at the bottom so that it then rises to the top and sinks when it cools. But instead of a heating source, we're going to go ahead and use our Alka-Seltzer. So let's do that and see what happens. I'll break up a tablet and put it in. So we can see that our Alka-Seltzer is foaming. It's creating carbon dioxide bubbles. And those carbon dioxide bubbles, which is the carbon dioxide trapped by our water, become less dense than our oil, and they float to the top of our vessel, and then that carbon dioxide gets released, and then the bubble is more dense and falls back down. Pretty cool, right? enjoyed that experiment, and I encourage you to go on our website and find some more home experiments that you can do with your family and your friends if you want. I'll hand it back over to Bassam.
Thank you, Amanda. That was pretty cool. I think that was really, really cool. And everyone should try this experiment along with other experiments that you can find on our websites. Always enjoy doing these experiments with each other. And if you have questions, you can send in questions, right, Dan? They can give us questions. We try to answer them now. But also, if you go to the website at the bottom of the homepage, there is an email address that you can use to send us information. We are always delighted to share the joy of science, the joy of learning, the connection.
And if anyone does have any questions, you can post them in the Facebook comments and we'll be able to answer those live. And as Bassam said, you can join on the website.
Between science, the arts, and humanities, in addition to the beautiful experiment that she shared with us.
I think we lost you for a second, Bassam.
Can you take? I was inviting you to furthermore show how we celebrate the connections between science and the arts and the humanities by asking you to do your next so-called experiment.
Okay. So as Bassam kind of said just now, I do some things besides science day to day. And one of the things that I enjoy doing is singing. And so I have prepared just a little bit of a song. The artist's name is Andra Day, if you're interested. And the song is called Rise Up. And I'll just sing a little bit for you all. You're broken down and tired of living life on a merry-go-round, and you can find a fighter, but I see it in you, so we gon' walk it out and move mountains. We gon' walk it out and move mountains. I'll rise up, I'll rise like the day, I'll rise up, I'll rise unafraid, and I do it 1,000 times again. And we'll rise up, high like the waves, we'll rise up, in spite of the ache, we'll rise up, and we'll do it 1,000 times again. For you, for you, for you, for you. Thank you.
Thank you, Amanda. And we always try to connect science and society. We try to look at the connections between science, the arts, and the humanities. And what I would like to show you here on the next slide, Dan, please, is a collection of the reactions of audiences that we've had in the past. You can just see from the facial expressions how important it is to pay attention so you can really learn and you can think about what you have learned. And that's why I would like to share with you next an experiment that we have on video.
For my next experiment, I'm going to use a beaker and mix in it different liquids. Turn the light on. Turn the motor on so you can see the bar spinning. And I need 2 more liquids that are right here. So what I do is turn this like so, and add the first liquid, that clear colorless liquid. I pour it in, and it gets a little cloudy. Then I take the second liquid, and I pour that in. And anything exciting happened so far? Well, the volume increase, that's not so exciting, you know, that's a common experience. Well, that looks like we have a tornado here, right, at the top of the liquid. I hope this is the only tornado you'll ever come close to. And I take the third liquid, and I add that. And there you see a change. So this is a beautiful experiment where we mix 3 different liquids, and we see that has been a change. What's going on? Are you seeing something that I'm not seeing? The last time I looked at the liquid in the beaker, the color was blue, deep blue, almost black. Tell me when to look. Should I look right now? I don't want to trip over anything. Tell me when to look. Should I look right now? Yes or no? No. Okay, I won't look right now. Right now? You sure? I don't want to trip over. Every time I look, it's deep blue, almost black. Maybe you can help me better on this side, okay? Tell me when to look. Right now, you sure? Don't want to trip over it. Every time I look, it's blue. All right, to help me out, tell me when to look. Right now, you sure? Right? Absolutely, right? What's going on here? What's going on? Oh, whoa. What is it that you were doing that I was not doing? You were looking all the time? I was looking all the time too, but I wasn't looking here all the time. Remember what I said before? Pay attention. Pay attention to what's going on so you don't miss out on the excitement of beautiful chemical transformations that happen when you mix chemicals together and you do experiments safely. This experiment is one of 50 known such reactions called oscillating chemical reactions. It was discovered by 2 high school teachers, and it's named after them. It's called the Briggs-Rauscher reaction. Briggs and Rauscher taught high school chemistry and physics in Northern California. And about 40 years ago or so, they published a paper in the Journal of Chemical Education describing this beautiful, captivating behavior.
Here we are back live with you from Madison, Wisconsin, the morning of Saturday, July 25th. Again, welcome to all, and I hope you're enjoying this program. Amanda and I, for sure, Dan also, and all the people behind the scenes are enjoying this. If you have questions, you have comments, please type them in and send them. So now I have a question for you. Here's my question. Do you always believe what you see? So I ask you now to focus your attention on this glass that I have here. Let me see if I can adjust my camera. There we go. And I have a card with 2 arrows. I'm going to take the card and put the card behind the glass that has a clear and colorless liquid in it. It's water. I'm going to lower this, and you tell me what you see now. What? What do you see now? Do you see what I see? You see the arrow is reversed? You think this is a magic liquid? No, it is water. That's why I ask you always, You always believe what you see. This is an experiment you can do at home. A glass filled with water, on a piece of paper, just mark two arrows. They can be the same color or they can be different colors. They can be turning this way, any way you want, and then position the paper about 10 to 12 centimeters behind the glass and lower it and see what happens. And always think about explanations for whatever it is that you are enjoying. And by the way, in my volume 5 of chemical demonstrations, we have in the first 80 pages of very good descriptions about color, light, vision, and perception. It's important that for us to understand how the brain interprets the visual and other information that we receive. But I refer you to this. It's available from the University of Wisconsin Press. Go to their website and you can find out how to obtain a copy of this. If you like to share it with your family members, you like to share it with teachers, with anyone you like, that's a very, very good source of reliable information. Dan, do we have any questions so far? Anything that Amanda and I should try to respond to, or shall we keep moving?
Well, people were fascinated that the arrows switched. And we've got some great comments coming in through Facebook. And if people want to comment any other questions or comments, they can feel free to do so. We do have some questions maybe about how people can do these experiments safely. And if you have any advice on how you do safety in the lab.
Safety is paramount in everything we do and everything you should do. Safety in handling chemicals, safety in doing everything that we do. That's why earlier on, I reminded everyone to put their mask on, especially with the horrendous danger from the pandemic. One can never be careful enough about this. When we do experiments, we always obey the safety rules. And the experiments that we are sharing with you this morning are experiments that can be done at home. They involve household chemicals. The experiment that Amanda showed you is just pretty cool, as she said. And the experiment with the water and the arrows on our website, scifun.org, SCIFUN. In the upper left corner, you can click there and download a whole set of experiments that can be done safely at home. And these have been tested and they have been enjoyed by thousands, tens of thousands, hundreds of thousands of people. So I invite you to try some of those experiments. And if you come up with some ideas for us that you would like us to develop new experiments, you do let us know about this. But always be safe, always do the experiment with another person so that you can both share the joy of learning and experimenting.
Thank you. And people are also very interested in a lot of these experiments that we've seen today have involved some beautiful colors. And maybe you can share a little bit with us about how these colors are produced and how color is involved in chemistry.
Well, color is a very important phenomenon. I'll tell you, I became interested in science because of color. When I was growing up in my native Lebanon, my mother knitted a sweater for me, a yellow sweater, and I wanted to know what yellow is. And she said the sweater is made of wool. And I said, wool comes from sheep and they're not yellow. So started asking questions, just like the question that we're dealing with right now. And this led to wanting to explain the beautiful, complex world that we live in. Why are the colors of the leaves green? Why do they change color in the fall? All such questions that are asked by youngsters, by adults, by grandparents are very important questions because they show us how curious we are, and we should try to satisfy that curiosity correctly. And once again, I invite you to visit the website because we have not only experiments you can do at home, but we have lots of other explanations. There's an entry called Learn About. Learn About has to do with, among other things, the changing colors of the leaves in the fall. So, light consists of, in the visible spectrum, consists of energy, and this energy generates signals when the light rays hit the retina in the eye. And then, as I said about hearing, I know I say similar thing about visual sensation. Beautiful chemical transformations happen, and they then the brain is able to assemble and put all these together. Speaking of color, what I really would like to do now is share with you another experiment that we have on video, and we'll come back and talk some more about color.
What I have in this bucket here is some carbon dioxide, except it's not in the gaseous form. It is in the solid form. It's called dry ice. So I put my gloves on, and I try now to get a chunk of dry ice and set it right here. This is solid carbon dioxide. It is at a temperature of minus 78 degrees Celsius. It's very, very cold. And that's why I wear the gloves. This solid is changing into a gas directly without melting. When a solid changes from being a solid to a gas without melting, we call that sublimation. Can you say sublimation? Sublimation. Sublimation is happening right now, but we can't see it. How come we can't see it? Because carbon dioxide gas is mixing with air, which itself is a mixture of gases. I want to ask you to focus your attention on what you see between my two hands right here. What shape are these objects? Cylinders. And how many cylinders are there? Six, and they have in them what looks like colored liquids. We know they're liquids because from experience, we know what liquids do when we shake them up. And they seem to be arranged in some kind of order. This pair has what color liquid? This one. This one. All right, so what I'm going to do now in this experiment, I'm going to take chunks of dry ice, and I'm going to drop them into these cylinders, and we'll see what happens as I drop the dry ice in every other cylinder, not in every cylinder. Does this help see it better? All right. Do you see bubbles? Those are carbon dioxide bubbles coming from the sublimation of dry ice. We see them there because a gas is mixing with liquid. Over here, we don't see them because gas is mixing with air. We also see beautiful color changes, right? And we see something coming off the top here. It looks like smoke, but it's not really smoke. It is a mist. It is the condensation of water vapor on the cold carbon dioxide gas that's coming from the sublimation process. But some of the carbon dioxide gas dissolved in the liquid and caused the color changes. So each of these pairs had in them dyes, and these dyes change color depending on how acidic or basic a substance is. To begin with, all the cylinders had in them a basic substance and different dyes, 3 different dyes. And then when carbon dioxide dissolves in water, as we have in carbonated beverages, we get carbonic acid. We drink carbonic acid. It's safe to do. But you see the color changes are because of the acid-base reaction that we have used. And these dyes, when they change color, they indicate to us that a reaction has taken place. That's why they're called acid-base indicators. They indicate a chemical change. Do you like this experiment? Yeah. Thank you.
And these beautiful color transformations we just saw on video are the result of the interaction of carbon dioxide gas when it is in water. the carbon dioxide gas came from the sublimation of the dry ice. You can tell, as you saw and heard me say on the video, carbon dioxide gas is not very soluble in water. If it were, we would not be able to see the bubbles, but carbon dioxide interacts with water. And carbon dioxide gas is a greenhouse gas. And greenhouse gases contribute enormously to global warming. That's why we should be very, very much aware of the consequences of using and depending on fossil fuels as energy sources for us, because the combustion reactions of fossil fuels that give us the energy that we need also produce carbon dioxide. And the amount of carbon dioxide in the atmosphere has been increasing. It's represented by measurements made at the top of a very high mountain in Hawaii by something called the Keeling curve. Let me try to show you. Can you see the Keeling curve there? This is a representation of the measurements that are made, and a very interesting rise in the amount of carbon dioxide gas coming from our over dependence on the use of fossil fuels. And that's why we have to mitigate global warming, and we have to be very, very careful about it. I say a few more things about this, but I also want to show you this map. Actually, there are two maps of the state of Wisconsin. These are the plant hardiness zones. And you can see from the color code that there is a change. And this change is a direct telltale of global warming. The fact that the zones are changing. These zones are telltales of the temperatures of the plants. And so it's very, very important for us to try to mitigate climate change and to take responsibility for using alternative sources of energy that are clean energy, that are economically feasible. And it's crucial that we face this grand challenge that faces us and faces the planet in responsible ways. That's why it's important to connect science and society. That's why it's important for us to understand the effective use of technology to help advance the human condition, to help advance the joy that we have in living on the planet, but to also be responsible for what we do as we use fossil fuels as sources of energy. Well, back to color for a moment. So color is fascinating, and it is something that we should consider, and we should think about what causes color changes, because color changes indicate to us that a chemical transformation has taken place. When you take a bite from an apple and you wait for a while before you take the second bite, or if you cut an apple, you see there's a color change. If you enjoy blueberries, if you use frozen blueberries as a source of the blueberries, and you put those in a dish, and then you add tap water to the after you finish with the enjoying the blueberries, you add tap water to the residue in the dish, you see a color change. Color changes are fascinating, and that's why I urge everyone to really have a good conversation with others about. So just remember, do you always believe what you see? So be thinking about the observations that you're making. And one more time, the first 80 pages of volume 5 in the chemical demonstration book series is about color, light, vision, and perception. So now we move to another video that we have we want to share with you. So here we go with the next video, and Amanda and I will be back shortly.
And I'm going to do an experiment with the hot boiling liquid that I have here. The one that I have here is water. I'm going to use my gloves now to protect my hands from heat. And I have some dry ice here, but actually I'm missing I'm missing a dishpan. Let's see if I can find it. Could someone please bring me the dishpan? Would someone please bring me? Hello, Bucky. Good to see you, Bucky. And welcome to my lab. Thank you. This is what I really wanted to do. So Bucky, would you like to help me with this experiment? You notice that Bucky is a good science student. He's wearing his eye protection. I want everyone to see that. And so, Bucky, here's what I'm going to do. I'm going to take the boiling water. I'm going to put it in this dishpan that you brought me. And what we see coming off the top here, what does it look like? Steam is invisible. You can't see steam. We see a mist. That's what we're seeing. The mist of water vapor. And then, Bucky, here's the experiment. You take this bucket right here, and you pour all the dry ice that's in there into the boiling water. Go ahead, Bucky. Do it, all the way, all the way. That was very, very nice, Bucky. Does that look like steam? No. It looks like fog. Looks like fog, and that's what it is. We just made a lot of fog here. You notice that the fog is moving downward now because carbon dioxide gas is denser than air. The condensation is on the carbon dioxide gas that's coming from the sublimation reaction.
Welcome back. I hope you enjoyed that huge plume of condensed water vapor that Bucky helped me prepare. Water vapor is another greenhouse gas. And water vapor, water is a unique substance. It's the only substance that exists in 3 stable forms on our planet: gas, water vapor, liquid, you know about that, and ice. And it's constantly moving between those 3 phases all the time. That's what the water cycle is about. And water vapor is a greenhouse gas. So we can't do anything about that. We can do something about other greenhouse gases. Let me just say to you very briefly that every molecule in the gas phase that has 3 atoms or more is a greenhouse gas. Yes, you heard me. Every molecule in the gas phase that has 3 atoms or more is a greenhouse gas. So water vapor representation is H2O. Carbon dioxide is CO2. Sulfur hexafluoride is SF6. Every molecule is a greenhouse gas, but they're not all consequential. Highly consequential. That's because they have a different lifetime in the atmosphere, and they also can react and disappear. But carbon dioxide is the main culprit, so to speak, that we have to be paying special attention to. So now what we would like to do is go to a different part of the program where we want to talk about the release of energy in the form of light. So we know about fireflies, especially in the summertime. By the way, did you know that there are no fireflies west of the Rockies? I learned this one time when I was giving a talk in California, and part of my talk was to say, hey, everybody knows about fireflies. And I kept talking about fireflies. And then someone, not one person, but several people came to me after the talk in the question and answer period and said, what are fireflies? I thought they were pulling my leg. Well, why aren't there fireflies west of the Rockies? So that's a question for you to think about and to try to find out explanations for it. So energy is released in a variety of forms: in the form of light, which is what we see; in the form of heat, which is what we feel if we're close to it. But there is also a phenomenon called bioluminescence, and that's what fireflies do. there's another phenomenon called chemiluminescence. And we're going to show you an experiment on tape about that very shortly. But on our Science is Fun website, in the Learn About entry, we have a couple of entries that Amanda is going to tell you about right now.
Thanks, Bassam. So in addition to learning about why leaves change color in the fall on our Learn About page, there are a lot of other Learn Abouts you can find. And some of them I've written recently about LCDs, or liquid crystal displays, and LEDs, or light emitting diodes, which are related to what we're currently talking about. And light emitting diodes can use the energy that they obtain from batteries, and we take one apart to show you what the inside of an LED display looks like. And they take that energy from batteries and they can produce light. And you can get multiple colors and combinations, and they're very fun to look at. So we have those in addition to other learnabouts up on our page as well.
Thank you, Amanda. So do visit our website, enjoy doing experiments, and do them safely, and ask questions. We learn by asking questions. We learn actually how to ask the question, but don't be inhibited at all in wanting to satisfy your curiosity. Why is the sky blue? Why do the leaves change color in the fall? How does the microwave oven work? What are the components of in our electronic devices, whether it's a telephone or a TV screen? How is it that we see color on the TV screen? So think about ways by which you can satisfy your curiosity and engage in conversations, in discussions, and learn more about the beautiful, complex world that we live in. Now, as promised, I'm going to show you on video a display of the release of energy in the form of light, but not in the form of heat. This is the phenomenon of chemiluminescence. So, Dan, roll the video, please.
For my next experiment, I'm going to use a very long spiral glass assembly that's connected to a funnel at the top, and at the bottom there's a large beaker. There's the funnel, spiral glass assembly, and a beaker, and I'm going to mix two liquids, a clear and colorless liquid with a clear and colored liquid, and I'm going to do the mixing in the dark. So can we have the lights down, please? All the way down. There you go. This is the release of energy in the form of light, but not in the form of heat. This is the phenomenon we call chemiluminescence. Chemiluminescence is related to bioluminescence, and most of us know about bioluminescence because we know about the firefly reaction.
Well, that was a fascinating display of the release of energy in the form of light, but not in the form of heat. And that spiral assembly, glass spiral assembly, using luminol, and that's the name of the chemical, and using hydrogen peroxide, that's the name of the other chemical. And all of these displays are the result of research and development that we do in my group. We spend a lot of time learning about the science behind the experiments, behind the phenomenon, and try to share it with you in ways that are pleasing and that are inviting to you to ask questions and to make comments. And I know from Dan that we are receiving questions and comments. Dan, maybe if there's a comment or two that you'd like to share with us, Amanda and I would appreciate hearing some of the comments if you have any, and if you don't, we can just I can go on to the next thing.
Yeah, there are so many comments about how much fun people are having observing these. So I wonder, you said earlier, and I know one of your mottos is to pay attention and to explore your curiosity. So maybe you could give some advice about how we can pay attention to experiments that we do, but also about just the world around us.
It's important to pay attention to what's going on, that you focus on. There's so many things going on all the time. The brain receives 11 million bits of information every second, and we have to train ourselves, and we have to learn how to sort out the information. So pay attention to what's going on in front of you. Try to make sense out of it. Think about the changes that are happening. Pause. Sit back for a moment and reflect. Write down your questions. Express yourself in writing. That's very important. And I mean writing by hand. I don't mean simply typing it on the computer. Because when we write by hand, it takes longer and it helps us articulate our thinking and express ourselves. And then do some, what really helps is rewriting. So paying attention means really being focused on what's going on and being interested in it and wanting to share what it is that you're interested in and wanting to ask questions about what's really puzzling you. It's very, very, very important that we do this, not only in science, but in everything that we do in life. It's so important that we enjoy to the fullness of life the moments that we have, not to only interact with nature, but to interact with each other. And in all of our interactions, we have to be respectful of each other as fellow human beings. Yes, some people have ideas that we don't respect, we don't agree with. That's okay. What I'm saying, we have to be respectful of each other in every conversation, in every discussion that we enter in. And there's so many different ways by which we can enjoy life. And Amanda, you have some strong feelings about this, right? You want to? Would you please share them with us?
Sure. I personally think that it's important to have one or two or maybe even more things that you enjoy doing every day and that intrigue you, that cause you to ask questions. You want to know why, you want to know more, and it's exciting. And it's important to have those no matter what they are. So for me, they're music, they're science, chemistry, things like that. I love teaching as well. And so those sorts of things are what help me get excited every day. And no matter what those are for you, I hope that you can find them and then keep with them.
Oh, thank you, Amanda, and that's a very, very important message for all of us. And congratulations again on completing your PhD and moving on to a teaching position at University of Wisconsin La Crosse, not too far from Madison. And of course, you'll still be part of my group. You're always welcome to be part of my group. And I uh, want to bring this part of the program to an end right now by, of course, thanking Amanda and thanking Dan and thanking everyone